Hello, I'm Professor Nicholas Solomey at Wichita State University, and today I'll be presenting on the topic of neutrino uh, from the galactic core being imaged by the gravitational lens of the sun. So let me share my file with you and ready to go. Okay, this project is also being done in cooperation with other faculty and graduate students at Wichita State University, NASA's Marshall Space Flight Center, North Dakota State University, and the Jet Propulsion Lab in Pasadena, California. Gravitational lensing is not a new idea. It actually comes from Albert Einstein, who predicted that the sun or any other very dark, dense object could bend space and create a gravitational focus of light. Uh, Light from, say, uh, any object, distant object, which is parallel, focused by the sun, would be somewhere about 550 to 700 astronomical units away. And there's a lot of papers out there that describe the optics of gravitational lensing. Landis at um, Glenn NASA Space Center in Cleveland is one of them, or uh, Slava at JPL is another reference that you could easily look up, and the references are included here at the bottom. The Hubble Space Telescope actually has some very nice images of accidental alignments of distant objects by a star. This particular image I chose because you notice that the ring it forms is not complete, and that's because there's a major off-axis. I want to emphasize this because some of what we'll be talking about later with the galactic core is also highly off-axis as well as on-axis. The direct object is actually seen above the horseshoe, and it's this small little line of blue stars. And then the star creating the gravitational lens is the bright object in the center, and you have this ring arc. The arc itself, notice there's a lot more light in it, and that's because the light collecting power of a gravitational lens is enormous, about 10 to the 12 to 10 to the 13. Um, so this actually tells us that we'll be able to collect a lot of light from a gravitationally focused object compared to direct observation. And it also demonstrates that off-axis is just as good as direct on-axis imaging. Gravitational lensing with neutrinos is a little different. The neutrinos have a mass, a non-zero mass. We don't know exactly what it is, but if we believe some of the estimates of the lower limits and upper limits, we can estimate that the neutrino has a mass that generates a gravitational focus much closer to the sun, somewhere around 20 to 45 astronomical units away. And unlike the light gravitational lensing, which is 550 to 700 astronomical units away, where no man-built spacecraft has reached yet, the Voyager space probe is only 165 astronomical units away from the Earth, and it's been traveling for almost 45 years. The distance of 20 astronomical units is the planet Uranus, and Neptune is out at about 30, and Pluto is about 45 astronomical units, just to give you a scale. So all those planets have been visited by man-built spacecraft, and these are achievable distances, 20 to 45 astronomical units. It's not unheard of in a spacecraft. Yeah, there's not a lot of them that have done it, but there's at least a good 6 that have. Now, the sun itself, when you look at our sun, it's not transparent to light. And so when you use light gravitational lensing, you actually have to put an ocular in there and block off the direct light from the sun. And you got to make it a little bit bigger than the sun because the sun has a corona. And you get to about 10 to the 12 light collecting power. But the sun itself is actually transparent to neutrinos. The sun doesn't, the solar neutrinos or stellar neutrino from fusion is not actually hindered by passing through the limb of the sun. That's why it gets out of the sun and gets to us here. So a distant object like the galactic core could actually have and we're talking about neutrino collecting power, which is similar to the light collecting power when you talk about focusing light, has another 2 or 3 orders of magnitude because the sun itself doesn't obscure the neutrinos, and looking directly at the sun and neutrinos at a very far distance like Uranus or Neptune is extremely small flux of direct neutrinos from the sun. And so that adds interest and insight into this. What did I do? 1, 2, there we go. So we're talking about making the galactic core as the object. We're talking about making the sun as the lens, and we're talking about making a planet or a spacecraft as the detecting media. Well, all planets orbit around the sun on the ecliptic, and that's the yellow line here. And at different times of the year, the galactic core, sun, and the alignment on the ecliptic, such as the Earth, is actually changes with time. Somewhere around early January, the yellow line passes through the galactic core disk. And also in the middle of summer, we actually have 3 pulsars, the Gamagan pulsar, the Crab pulsar, where the ecliptic is right opposite of it. So it's possible to make a telescope, such as a neutrino telescope, that actually could, at different times of the year, focus this. Okay, so the galactic core itself is fairly large. The galactic core is about, if you were able to see it in visible light, is about 2 moon diameters across. And so it's a broader source than our sun, but not that much broader. And of course, we could have direct imaging and we get off-axis imaging, as we demonstrated with that Hubble ring lensing earlier in this presentation. And so due to the large angular extent of the galactic core, you could actually get, which is twice the diameter of the moon, you could even get a larger number of neutrinos to be concentrated at the neutrino gravitational focus for off-axis rays. So our planned study as we proceed in this is we'd like to know how many stellar neutrinos from galactic core stars are at the neutrino gravitational focus. We also want to know how many neutrino of very high energy are at the galactic focus. These would be sources in the galactic core which have accretion disks around neutron stars or black holes. And these, when this matter falls into the accretion disks, we actually then generate a neutron, and we also generate neutrinos being isotropically emitted. And can we do a direct detection of the neutrinos? And can we, or another option is, can we use a gas or ice giant planet like Neptune or Uranus to increase the detector mass to see galactic core neutrino interactions? We've actually done some initial estimates of fusion neutrinos from the galactic core. We used the model of stars in the galactic core and their distributions by Kent in APJ volume 378. It's just called Luminosity Model of Milky Way, and it was in 1991. And we've also estimated using the absolute magnitude of stars to figure the number of neutrinos compared to our sun. Now, of course, this is completely wrong, but it's actually wrong in that it's always low. Some of the larger stars are going to have larger atmospheres. A lot of the light won't make it out, but neutrinos will make it out. So we estimated with this technique, the absolute magnitude of the stars was used to determine the amount of neutrinos coming from it. And then we integrated over all the stars that were there, which, by the way, is a lot of stars, according to the model Kent. We corrected for the distance to the galactic core at 25,000 light years. We used the light collecting power of the gravitational lens at only 10 to the 12, which is what light is. The neutrinos going through the limb of the sun increases this a couple orders of magnitude, but we didn't incorporate that because we wanted to have an estimate that was couldn't be argued with too much. We used off-axis stars with light reduction out to all the way out to 1 degree. And we have to assume the size of a neutrino detector. And for now, we just assumed in this calculation that the neutrino detector would be 4 meters across and 8 meters long. It's a fairly large volume, but it's the size of a spacecraft upper stage fuel tank. And from all of these assumptions, which, as I agree, they're just estimates. And by the way, this is the estimate we used in our proposal to NASA for this to get this funding, is that the number of galactic neutrinos at the gravitational focus with this size detector volume is somewhere between 800 to 8,000 times more neutrinos than at the surface of the Earth directly from our sun's fusion process. So 8,000, 800, these are two numbers that we feel confident in for this estimate. And like I said, in point 2 there, we're certainly low because we use the absolute magnitude of stars. And we also used we didn't use into account the entire light collecting power or the neutrino collecting power of the gravitational lens being able to go through the limb of the sun, which buys you another couple orders of magnitude. So it actually could be bigger by at least 2 orders of magnitude than 800. It could easily be 80,000. And this estimate was a senior thesis student by Lynn Buchel at Wichita State University with me. And she did galactic neutrino lensing by the sun, an initial estimate for her senior thesis project in 2018, which I thank her greatly for her time and efforts to work with me on this. So there's also the possibility to have high energy neutrinos from the galactic core. The Chandra X-ray telescope has shown that the galactic core has 1,000 to 10,000 accretion disks of neutron stars and black holes. As matter falls into these objects, the protons and electrons make neutrons and neutrinos that are isotropically emitted. These would produce higher energy neutrinos than can be, which can convert into muon tracks because they're higher energy. Don't forget stellar neutrinos in solar fusion or stellar fusion processes are low energy neutrinos that don't have enough energy to generate muons when they convert. The galactic core, shown here as a red dot, is located at 19 hours 45 minutes and minus 13 degrees declination. Opposite the sun would be 7 hours 45 minutes at the plus 13 declination. So there's the possibility to use an upcoming transit of Uranus or Neptune such that the galactic core alignment with the sun, with the planet Uranus or Neptune, would pass through this. And you can see the years at which this will occur. Left is a track of Uranus passing through the night sky, and right is Neptune. And somewhere around the year 2035 and 2065 is when the alignment of Uranus and Neptune will be just opposite that of the galactic core from our sun. So those are large objects. And so if we didn't want to actually take a very large detector, such as 4 meters across and 8 meters long, which, by the way, could be smaller if our neutrino estimates are wrong and are actually higher, which we're hoping for. But the other thing we can do is use an orbiter around Uranus or Neptune, such as upcoming missions to Neptune with the Neptune Odyssey project of Johns Hopkins University's proposal at the APL. And we'd like to answer some questions in these as we continue this study, such as how much light would there be in the atmosphere of the dark side of Neptune or Uranus from high energy neutrino conversions? What optics imaging systems would the orbiter need to have that they don't already take with them, such as filters or enhanced light collection power area? And how close to the gas giant would the spacecraft have to get to do some of this? Would it be a standard orbit from very far away, or do you have to get really close? All these questions are planned to be studied in our upcoming 1-year study. And I've depicted the process here of a stellar core being imaged by the sun, and at the planet Uranus, the neutrino acts in the dark side of the atmosphere near the surface and generates a muon track, which we can visualize with an orbiter. What are some of the sciences possible? Well, there's lots of astrophysics that can be done. We can measure the neutrino intensity of point sources, maybe like the Crab and Jaminga pulsar. I would love to measure the number of galactic core accretion disks and structure in the galactic core. And so those are astrophysics possibilities. There's also the possibility that this project could result in a new way to do elementary particle physics. After all, the exact location of the galactic neutrino focus around our sun is dependent upon the mass. So if you don't know exactly the mass, but you could determine and measure directly where the galactic core neutrino focus is, then as the spacecraft goes away from the sun, the solar neutrinos would drop off. And at some point, as you approach the galactic core neutrino focus, somewhere between Uranus and Pluto, then you would see a peak as you increase the rate of neutrinos. So conclusion, what was presented here are some ideas and initial calculations and simulations for our funding proposal to NASA's Innovation Advanced Concept Office. Our $125,000 funding from NASA starts in May of 2021. We will improve the simulations, answer more questions, and determine how feasible these ideas are. Especially, we're going to plan to redo the calculation of neutrinos from the galactic core and to complete the integration over all the stars, as well as try to start to simulate some of the ideas of accretion disks of neutron stars and black holes. So stay tuned for future updates as we start this one-year study in a few months. Thank you.